Hello again. Today we'll talk about object detection with transformers, and we'll discuss the architecture of a particular model that does that, called DETR, which was created by Facebook researchers. So transformers came out in 2017. Since then, got a reputation of a sort of heavy artillery. So it's an incredibly big module. It's heavy, it's slow, but it makes everything better. So let's see how it performs in object detection. And also, this model is particularly famous for simplifying the approach to object detection. So popular models before that, like YOLO or regional proposal networks, they were either multi-stage, where first you have like crude estimation of bounding boxes, and then you refine them through applying a different detector several times, or you have a lot of handcrafted components, like in YOLO, for example, and DETR instead replaces them with just a model. So you have a model, you feed in the image, you get bounding box predictions as the output, and no intermediate steps, no handcrafted components, just the model. And that is simpler and more beautiful, I would say. So first, a reminder, I am making a series of such videos about computer vision. So the idea was to start with something really simple, like digit classification. That is basically an introductory level tutorial that you can just sit down and go through yourself in half an hour. Then we threw in a bunch of deep learning stuff on top of that to make the model bigger and better. And that is convolutions, activation functions, optimizers, patch normalization, residuals. And finally, we ended up training a proper ResNet model, analogous to a winner of ImageNet competition from 2015. It's also important to understand that the difference from digit classification to ImageNet is more or less quantitative. So we had image classification before, and we still have it in ImageNet. That just the number of classes and the data set got bigger. Sure, it took a lot of research, a lot of years of scientists trying to come up with these architectures, but more or less the setup for the model was the same. And that is mainly because in ImageNet, in image classification, you still classify the image as a whole, sort of assuming that you only have one object on the picture. Now, if we move on to object detection, where you can have many objects or you can have no objects at all, and you need your network to be able to deal with that, then it becomes a bit harder. And we've discussed approaches to do that. So first one, which is probably the most popular at the moment, is called YOLO. And it's quite good. It has its problems. It's not as accurate as state-of-the-art models, but mainly it is really fast. So YOLO stands for you only look once. So it's a single stage detector, a quite lightweight model. So it's quite useful at the moment for different real-time applications. We also trained our own YOLO from scratch on the COCO dataset. We've read the source code to understand it more. And now we are discussing this second approach to object detection called DETR. So here is like the overview of the field, I would say. So this is a screenshot from the Papers with Code website, and it just shows the leaderboard for COCO Object Detection Challenge. So you can see here that it started in 2015. Since then, the average precision improved by quite a lot. And so YOLO that we've discussed before, it came out in about 2022 and has 57 average precision. And the DETR that we are going to talk about now, it only has 40 average precision, and it came out a bit earlier. So you can think of this as maybe a model that is slightly worse, but then a lot of stuff that came out after that, like deformable DETR, core DETR, which is currently a leader with 66 average precision, they all basically use the same idea, just explore it a little more and add some more stuff to it to make it better. So in this sense, DETR is more like a proposal for the way to train models that is then used by different teams to train their own good model than like just a good object detector in itself. And here is the plan for today. So we'll start with motivation, which is basically what are the problems with the previous approaches that we are trying to solve here. Then we discuss the loss and the overall setup of the model, that is direct set prediction, so how to make the model just predict a set of objects directly with no external, with no multiple stages, no handcrafted components, and so on. Then we dive deep into model architecture. So we start with just describing what is a transformer and why do we need a transformer. Then we discuss the multi-head attention, self-attention, cross-attention, encoder-decoder, and positional encoding. Finally, we do some analysis. So we will actually look at visualizations of attention masks, how cool it looks like, and what important conclusions can you do from there. Right, and first, motivation. So why do we think that we need to change something about object detection? Here's the example of YOLO model. So it takes in an image, passes that through a series of convolutions, and then the output is this cube of results where every cell, this row within the cell, has a lot of predictions for bounding boxes and class probabilities. And then there are many cells, right? And every cell also does predictions for different anchor boxes that is not drawn here. But the problem is that you might have neighboring cells detecting the same object. So it's a known problem in YOLO. If you just do it naively, like this, you'd see that the same object is detected twice with pretty similar bounding boxes. And to get rid of that, we use a handcrafted component called NMS, non-maximum suppression, that just looks at predictions for the same class with a certain overlap of bounding boxes and just removes duplicates, right? And that approach has problems, right? So the actual YOLO v5 model that we've talked about before, it uses the intersection over union threshold of only 0.45. So it's slightly less than half overlap. And in the image like this one, where you have a lot of people crowded together in a tight spot, a lot of overlap between bounding boxes, the model fails to detect this man, for example. And this is a fundamental problem. If you think about this, the entire deep learning was science that needed to sort of step away from handcrafted rules and just let the model do the job for us. And here we are back at it with the model, but then we have a bunch of handcrafted components on top of that. And they are simple, they are too simple, so they work, they don't work in some cases. Here's another model called Regional Proposal Network. So arguably it works a bit better. So it has two-stage detectors. So the first stage generates proposals, and then the second stage sort of applies slightly different detector on top of those to refine them, to make them more accurate, and maybe to filter some of them out. So this one has more accuracy, but then having this multi-step approach is difficult. So it's hard to train because this sort of candidate selection operation is not differentiable. So you have to train it into steps. First you train the proposal network, then you train the detector network. It's also longer during the inference because you apply the model several times and you have to wait for the results. So you apply them in sequence. And because of that, it's not applicable in real life situations like robotics, self-driving cars, and so on. And so DETR was supposed to solve that. So let's see how it's supposed to work. This is the architecture of the model. This is a screenshot from the original paper. So let's go through this real quick. So we start with an image, then we feed that into a convolutional neural network like ResNet50. So as I said before, I have a detailed video about how to train an actual ResNet. But basically you just apply a set of convolutions one by one, thus downsampling the high resolution image to something like 20 by 20. At the same time, you increase the number of channels to something like 2000. Making it like this condensed representation of the image. Then you take these pixels and just flatten them out. Then we feed them into this new for us transformer encoder-decoder block. And the output of that are just tokens that are supposed to represent objects. So each of these tokens has a set of numbers 4 of them will correspond to bounding box coordinates, and then something like 90 for class probabilities. And the main thing we want to achieve here is that we predict the set of outputs directly. Directly meaning that we don't have extra conditions like that this output is bound to any specific cell or any specific anchor box. No, we just want it to predict basically anything the model wants. And we want it to be a set. So we want the loss to not penalize the model for outputting the correct output, but in different order. So we want it to sort of ignore the order completely. And that is achieved by bipartite matching loss. So let's talk about that. If you think about it, the problem is not so simple. So here is the potential predictions they may come out of the model, especially when we just start training and the model outputs a lot of random stuff. So originally we had just 2 birds, and now the model predicts 3 objects. So the first one looks to have more or less correct bounding boxes, but then the class is incorrect. Then the second one is a bit better in terms of, a bit worse in terms of bounding box, but now it correctly says that it's a bird. And then for the third one, the bounding box is completely off, but then it says it's a bird. So we need some sort of loss that would correctly assign the bounding boxes to the objects in such a way that to make the model trainable and to make it output what we want. And the solution comes from graph theory. So bipartite graph is a special case of graph where you just have 2 columns of nodes. I remember we had that in computer science class in college, and back then no one quite understood like why do we even need this, and now it turns out that there is a case for that and it's useful. And the problem is usually formulated something like, we have job applicants and jobs, or actors and movies, and we want to assign them to each other somehow. So we want to assign actors to movies such that every actor is only starring in one movie, and every movie only has one actor. And we want to optimize for something, some score function that we want to maximize or minimize. And you can easily see one solution. You can just brute force your way into it. You can iterate over all possible combinations and just choose the best of them. There's also a more optimized solution that's called the Hungarian matching algorithm, which basically does the same but more effective. And the solution is, we'll not talk about the algorithm itself, but what you get out of that is that this set of connections that connect nodes in the way we want. So every node from the left column is only connected to one node in the right column, and so on, and it optimizes some sort of loss. So in our case, the actual loss for 2 connected nodes will consist of 3 terms. So the first one for classification, which is the typical cross entropy. So it will look at the predicted class probabilities and compare them to ground truth. And we have like our normal class labels like bird, person, train, and so on. And we also have this special class called no object that is also just part of the classification. So this is one of the differences with YOLO. YOLO needed a special objectness loss and confidence to deal with the fact that there is no object being predicted by this particular cell. In here, we just make it a part of classification. And then we have 2 terms corresponding to bounding box predictions. So L1 loss is basically how far the actual predicted coordinates are from the truth. And then GIAU, which stands for generalized IAU, intersection over union, is a differentiable variant of IAU so that we can use it in the loss. And it corresponds to just basically overlap of the bounding boxes. And so we define this loss that depends on a particular set of connections. Then we activate our Hungarian matching algorithm to find optimal matches between left and right nodes according to this loss. And now it will look something like this. So the first cat matched to no object, the bird matched to bird, another bird matched to bird, and then everything else matched to just no matter. Now, this loss has all the qualities that we've needed. So first of all, it allows us to predict a set. So the loss itself doesn't care about the order of the objects being output by the model. So if you've noticed here, this bird moved from this position to this position, but the Hungarian matching still connected it to the first bird because this is the optimal solution for this problem. And so the final loss is still the same. So the loss doesn't care about the order of the objects. It doesn't change if you reorder them. This loss penalizes phantom objects in the background. So this cat, for example, here, there's no cat in the image. And so we had to connect it somewhere. And in this case, we connected it to no object, this special token that corresponds to no object prediction. And because cat class is not the same as no object class, this penalizes the model. So this loss penalizes phantom objects in the background. It also penalizes duplicates. So if we have 2 birds in the picture and the model predicts 3 birds, 2 of these birds will be correctly assigned to some objects. And then the third bird will have to be connected to something. In this case, no object, which is again is being penalized by the loss. And finally, we do the prediction in single stage. So we don't have any post-processing stages. We don't have any handcrafted stuff to do here. We just feed in the image, and the model just outputs exactly what we want, which is just beautiful. We just get bounding box predictions, class probabilities, everything we need, and we don't have to do any processing on top of that. However, there is a problem. So this sort of direct set prediction, like why didn't anyone think about this before? Well, it's hard to say, but at least one problem is that it requires node cooperation. So if you think about how a typical convolution looks like, so some output pixel in the layer is basically achieved by applying this kernel on a set of pixels in the previous layer output. So we have something like 3x3 convolution, which means that the receptive field is this 9 pixels that are somehow aggregated together to produce this value here. And then this value here is produced by this receptive field. So you have this connection of the pixels in the next layer output to the previous layer output, but then we do not have connection in between pixels of the same output of the same layer. However, we need the model to be able to not output any duplicates. So think about the following problem. Let's say you have a classroom and the teacher asks the class to provide exactly 2 volunteers for something. Now, if the students can communicate to each other, maybe see who raised the hand or something, then they can solve this problem without any problems. So they can just look around and see, okay, yeah, now we're 2, now we're 2, okay. If you can't communicate, for example, if you need to write your name down if you are a volunteer, and the class still needs to output exactly 2 volunteers, it will be impossible. So the best you can do is just to randomly decide if you put your name down or not, which sometimes will lead to class providing 1, maybe 2, maybe 3. So it will have mistakes. And the reason for that is that you cannot look around, you cannot see what your mates are doing. And this is how it works in convolutions, and this is how it works in just dense layers. Fortunately, transformers provide exactly this kind of interlayer communication that we need. So now let's talk about model architecture and transformers. First of all, transformers are actually about attention. So they were introduced in the paper called Attention is All You Need. And you can think about attention as something like reducing the noise, maybe ignoring some stuff. So think about just a noisy cocktail party, and there's a lot of conversations going on around you, and you need to focus on what your immediate partner is talking about. So attention is not providing you with any extra information apart from what you are hearing already. Instead, it ignores some of the information so that you can focus on the important information only. And so there's plenty of examples where that might be needed in imaging. So the bottom example is actually a modified version of MNIST that we've looked at before as well, which is from a paper that actually researched attention in the years before Transformer. So it's sort of one of the foundational paper for all of this. And what they did was they just generated a cluttered version of these images with like extra clutter here, 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 and so on, and then try to come up with good techniques for the model to be able to handle that. But obviously, if you just ignore all that clutter that happened in the background, then just you should be able to do that the same way we did classification on the MNIST initially. You can just look at the random image and think about how would you classify this. So this is the photo of a leopard. And so you'd probably just immediately notice this outline. You'd probably look at ears and maybe the nose and whiskers to understand that it's some sort of a cat. And then you'd focus on these spots and then just immediately say that it's a leopard. Here's another example from the original paper about transformers. So it was actually talking about translation. And here we have a sentence in English being translated to French. And you can notice that in most of these cases, the translation is almost word for word, except for this European Economic Area. And this one, European goes forward a little bit, and economic goes in the middle, and the area goes to the first position. So it's sort of a swap happening here. And this can be thought of as, like, when you generate this part of the translation, you can only focus on this word, and that's enough. But then when you generate this part of the translation, you need to focus on these three words at once. And this is what actually happened in the model that they were training. So this is another example of how attention can be used for translation and working with text. Before looking at actual transformers, we need to understand inputs and outputs. So transformer is a sequence-to-sequence model. So the input to the transformer is a sequence, and the output will also be a sequence. So let's look at some examples of sequences. So in our translation example, we have a sentence. And in neural networks, you usually convert that to something that can be used in neural networks using embedding lookup. So you basically have like a 256 dimensional vector representing each unique word, or maybe each unique token, where a token can be like two words at once, or maybe a part of the word is also a token. But that doesn't really change much. Basically, you have tokens, a set of tokens in the input. You do embedding lookup to convert that to a sequence of vectors. So every token got translated to one vector, and now you have a sequence of them with dimensionality s times e, where s is the sequence length, and then e is embedding size, which is 256 in this case. This is how it will look like in images. So we started with an image, passed that through our convolutional neural network, and got this cube with basically this small representation of image. So I'm plotting it here as a grid, but it's not actually a grid on top of this high resolution image. Instead, it's just a really small set of pixels. But each pixel is still somehow representative of this area of the image, as we will see later from the actual attention visualization. So, for example, this pixel really corresponds to this area with the head of the bird. And it also, thanks to a bunch of convolutions applied, it actually gets the context from the entire picture. And then you also have this channel dimension with a lot of numbers for each pixel. And to convert that to the sequence, you just flatten it out. So you had like height with picture, and then you get this sequence length being equal to height times width. And now the core of it, the meat of the presentation, that's attention. So this is the screenshot from the original paper. So in the beginning, we have just a sequence, and then we pass that through some more dense layers to project that down to our three important components, that is query, key, and value. Query and keys are used in conjecture to form a attention mask, which is calculated by just calculating the dot product between every possible key and query combinations. And then once we got that attention mask, we now get the values and do something like a weighted sum of these values to get the output. So let's now see how it looks like in detail. So the first step is queries and keys. So let's say we had our sequence that we got from the image, from the actual pieces of our bird and the background. And in this example, it's something like 28 by 28 in this downscale representation, which ends up being 784 sequence length. So it's quite long. Then each of these is independently projected into a query and a key. So we start with the, like for this element in the sequence, we have just one vector, but then we project that down to two different vectors for query and the key. And then basically what we do is we calculate the dot product between all possible combinations. So we calculate dot product between these two, between this one and itself, between this one and this one, this one and this one. And we do that for all the elements in the sequence. So everyone to everyone, every pair will be calculated. So the dot product is an operation that turns two vectors into a number. So it's a measure, it's calculated as just a sum of all the products between the elements. And you can think of it like in geometry terms, it corresponds to orthogonality. So dot product is maximum if like a vector represented by the first set of coordinates is orthogonal to the vector represented by the second set of points. And you can think about this as some sort of maximizing the signal in between these vectors. So they have to match somehow for this dot product to be maximal. And it's also sort of important to understand how many numbers come in and how many come out. So we had 256 dimensional vector for query, 256 dimensional vector for key, and that after dot product, there's just one number that is represented by one pixel here. So it's really not a lot of information getting passed through. So it's really all about sort of being able to represent this dark pixel here that says that you should ignore some stuff. So we need this dot product to be able to ignore stuff, basically. So this is the actual attention mask from our bird picture. So by doing this, each one to each one dot product, initially we had 748 sequence length. So attention mask will be 784 by 784. So it's like our picture squared. It's a bit hard to imagine that, but you can sort of slice it and just look at one row, for example, corresponding to one pixel for the query, and just plot this attention mask for every connection. So we can say that this pixel is like this head here, and then every other pixel will represent the attention coefficient of this pixel to every other pixel. So for example, this dark one here might correspond to attention between the head and this piece of background. And then this one is the body of the bird, so it corresponds to this one, to attention between this one and this one, and so on. Another interesting detail here is that you can actually see the outline of the bird in this attention mask. This is quite cool because, remember, we trained the model on bounding boxes, so we do not actually give it the information about segmentation, about the actual pixels belonging to the object. We just say that the bird, the ground truth bird, is somewhere within this rectangle. And still the model is able to learn what is object and what is not. So it is able to sort of create this pixel segmentation in a semi-supervised manner. It did not get that as a label explicitly, it learned that on its own. Another interesting detail is that the complexity of the time complexity of the calculation is now quadratic from the sequence length. So because we do this sort of dot product for every possible pair. If you increase the sequence length by x2, the total complexity grows by x4. So it's quite tough. And because of this, transformers are quite computationally expensive. And in the case of imaging, it's even worse because the original image, so the sequence is the actual 8 times width. So if we started like with a really downscaled image of 28 by 28, that gives us 784. If we increase resolution by x2, turning it into something like 50 by 50, the sequence length now grows by x4, and the overall time complexity grows by x16. So it's now insane growth. And because of that, this sort of DETR model is not able to handle really high resolution feature maps. And because of this, as we'll see later, it will have trouble with some small objects. But in later research, people found ways around that to make it even better. All right, so now we have this attention mask, which can be thought of as just basically this dot product between every possible pair. Now we use the third component, value. And this is denoted by matrix multiplication here. But basically, to generate this element in the output sequence, we now look at the sort of row in this attention mask, which will look something like this, which basically says, so again, this is the attention mask between this head of the bird to everything else. And now we just do the weighted sum. So maybe this tail of the bird corresponded to this element in the sequence, this beak corresponding to this element itself, and then maybe this one is corresponding to something in the background. And so you take a value from all of these and you sum them up. And the sum, since all of them had the same dimensionality, 256, the sum will also have the dimensionality 256. So you get this output element with the same dimensionality. So maybe in this case, this attention to self had something like 0.01 coefficient. It's quite small because we normalize them, so the sum is exactly 1. So this one in the background maybe had something like 0, and then this one over here had something like 0.2. So we sum these values for these elements with these coefficients to get this output sequence element. And again, we repeat that for everything in sequence. So the result of the overall computation is that we started with a sequence with a certain length and a certain embedding dimensionality. We apply this sort of attention mask calculation and then apply the value to get the weighted sum out. Result of this is the sequence of the same length, of the same embedding dimensionality. So we had this sort of information exchange between all the nodes. We had the detention where we got to ignore some of information, allowing this particular element to focus on something more specifically. And it's a layer. So we can sort of stack them on top of each other because the output shape and input shape are the same. Now, if you know something about deep learning, you know that researchers will not stop on that. So we have multi-head attention, which can be seen as just sort of applying several attention operations in a row, in a sequence. So basically you have 8 attention heads, which means that you would have 8 independent values, keys, and queries. You'll get 8 independent attention masks. You'd do this sort of weighted sum operation 8 times and get 8 outputs out. And then you just concatenate them all to get your sequence. And basically this allows you to capture the fact that maybe there's more than one thing going on in the picture. So you might need more than one attention mask to sort of correctly connect everything together. Other than that, it works pretty similar. So this was for the self-attention part. Now we're ready to look at the entire model architecture in a little bit more detail. So we've talked about this backbone before. So we feed in the image, we get some compressed representation with less pixel resolution. Then, if you've noticed here, we basically achieve the sequence by just flattening out the image, which means that we don't really know which pixel came from where. We lost this sort of positional information. And because of that, we need to sort of encode it in some other way. And I'll show you exactly how a bit later. But basically, we have this extra positional encoding, which is also represented as a vector of the same dimensionality, 256. And we just add that to our initial sequence elements. So every sequence element will have its own unique positional encoding embedding, which will represent the positional information. So then we get this sequence. We do the encoding step, which is basically this informational exchange within the parts of the image itself. And the output of that is of the same shape. So it still has this sequence of 784 elements. And we call that memory. So this is like the fixed output of the encoder. And then we have the decoder. So now we have these object queries coming in. And you can think of object queries because the output of this is basically the actual classes and bounding boxes. So you can think of these queries as basically experts, like coming in and taking a look at the image and trying to analyze what's going on there. So maybe this guy will focus more on objects in the down left corner and maybe on cats. And then this guy will focus more on birds and people and so on. We don't explicitly encode that. So instead, the actual queries are just random vectors constructed at first. So again, we use the same dimensionality. So every query vector is it has 256 numbers in it. We just initialize them randomly and just let the model train them as it sees fit. And we also have this sort of side input from the encoder. So we'll discuss it now. So it's called cross-attention. So let's see how that happens. So this is cross-attention. Now we have keys coming in from our picture, which is 784 sequence length. And then we have these queries. And let's say we have 100 of them. And they basically represent these experts that try to understand what is going on in the picture. So first we do the same operation with dot product to get this attention mask. But now instead of 784 by 784, it is 784 by 100 because you only have 100 queries. Other than that, it looks pretty similar. So this is the actual image for our bird, but now it's attention for one of the queries. You can also spot some differences here. So in encoder, in self-attention, it sort of looked like just outline of the bird. And here we can see that the expert is focusing more on the head, tail, and legs. And the reason for that is actually quite simple. So the output of the model will be the bounding box. And these parts of the bird are basically adjacent to the bounding box. So to properly draw this line here, you need to understand what's going on in the legs, like where do legs stop and like background starts. And because of that, to draw the bounding box, you need to focus on this extreme positions of the bird more than on something in the middle, for example. So now we have this non-rectangular matrix, attention mask of 784 by 100. And now again, we take values from the picture sequence. So it's 784 again. So we do this sort of weighted sum, which is called matrix multiplication. And the laws of matrix multiplication is basically that you multiply this by this, and then the common dimension goes away. So the output is just 100. So we came back to the dimensionality of queries, which also explains why this sort of part from the image is pictured like a side input. Because now this layer, it receives queries from the bottom, and it outputs something in the same shape as the queries. And this side part from the image that gets the keys and values it's sort of not affecting the shape of the output. So now we can sort of redraw this model architecture in a little bit more detail. So we have our initial picture, positional encoding. We pass that through encoder. We get our sequence that represents a refined representation of the image. Then we have these randomly initialized queries. And then we perform this cross attention. So again, for attention, we had queries, keys, and values. And so in cross attention, queries will come from queries. And then keys and values will come from the picture. But we also have this self-attention that helps sort of exchange information between these query experts and so on. And as usual, we have residual connections. So there's quite a lot going on there. So for example, one question you might have is that in here, the actual attention mask used queries. So the queries were only used in getting this attention mask, which are only used to basically reduce the contribution of some of the areas. But then the content itself came from the picture. So basically, there is not much the query can contribute here. But then we also have this residual connections, meaning that initial queries also sort of got summed up to the final output. And we also had this self-attention. So there's basically contribution from all this stuff happening at the same time. So this was my explanation of transformers. Transformers is one of the harder topics in deep learning to understand. So let's just go through all of that in one more time to maybe answer some of your questions. First, we had this attention mask, and that we used then in generating the output using values, right? So let's imagine what will happen if instead of this query.product to key operation to generate attention mask, we just use the fixed identity matrix. Identity is the matrix where on the diagonal you have all the ones and then everything else is 0. And in our attention case, it basically corresponds to the case where the attention coefficient to itself is exactly 1, and then to everything else it's 0. So then what will happen when you generate the output sequence is that you just use this element, you project it down using one dense layer to the value, and then that is exactly the output. And then this sequence element will get projected to its own value, and then it will be transferred directly to the output. So now it looks something like 1v1 convolution. So you are doing some sort of transformation. You are not exchanging information between parts of the image. So it's almost like 1v1 convolution, except that it's not operating on the 2D image. The positional information was lost. If we had just the matrix of ones, for example, so on every position, 1, 1, 1, 1, and so on, which corresponds to equal attention weights between every possible pair, including to itself. That will not be fully connected layer, although it sort of looks similar, of every element in the sequence being connected to this output. And it's not fully connected layer because the dense layer used to get this value is now equal for all of them. So the weights that you got to project down to the value are equal for every of these connections. And in the proper dense layer, they use different weights for every sort of neuron in the input. So this is the difference. Now let's talk about positional encoding. So again, when we did that flatten, when we created our sequence, we lost all the position information. So now we need something extra that we can use to keep that information, to provide that to our network in a different way. So let's start with a simpler case of just one-dimensional positional encoding, like for our translate task here. So we'll have them in the same shape as the sequence. So if the sentence has 60 tokens, then we'll need positional encoding of length 60 as well. And every element will also have the same embedding dimensionality. So we'll need a vector of 256 numbers. So really, there are different ways to generate this embedding representation of position. There is a quite good article that explains that I will link in the description. It has some beautiful math in it, so if you're really interested, then do check it out. I'll do a quick explanation here. So basically, we have these 256 numbers that we have to initialize somehow. And there are some requirements that we want. So we could have gone for something like just numbers from 1 to 60 or whatever was our sequence length. That's not quite good because it's not normalized. The values will depend on the overall sequence length, and they're not from 0 to 1. They're quite big. Neural networks don't like that. Also, we want these embeddings to make it easy for the network to represent relative position. So we are more interested in relative positioning. So like what is to the left from this word, for example. And we want some way to encode that into embedding so that it's easy for the network. So one solution to this, which is quite easy to understand, is just learnable encodings, meaning that we have these vectors, we just initialize them randomly, and then just let the network decide for itself what it wants to put in there. And it's able to do that quite well. It's not the best choice, but it works. Another solution is sine-cosine positional encoding. So this is approximately how it looks like. So basically, we have 256 coordinates within the embeddings representing the y-axis, and then the position within the sequence representing the x-axis. And so this bottom one here is like a sine function with quite high frequency. And then the one in the middle is just the same one but longer, and then the one at the top is maybe just really, really long sequence that changes only slightly as you go forward. So this way, sort of, at least the top one, you can already get precise position out of that. So if this encoding has excessive information, these sort of different frequencies of sine and cosine can be visualized as just different knobs. So imagine that you need to set up some value with a lot of precision and a lot of range. So you have the first knob that is like really insensitive, meaning that if you turn that a little, the volume goes up by a lot. And you have this second knob that is slightly more sensitive, so you can turn it much more, and it will allow you to adjust the volume in with a lot more precision. Then you have another knob with even more precision, and so on. So having this combination of knobs lets you set the value in a huge range as well as with a lot of precision at the same time. And also, since we wanted originally to be able to represent relative position, the sine and cosine are really good at that. So the actual formulas look really beautiful for sine and cosine. So you can sort of infer the relative position of two elements using just simple transformations on top of these embeddings. So another point worth mentioning is this plus operation. So like what that even is. Like why don't we like concatenate the positional information to content information, for example? Well, the one reason for that is that it's expensive. Transformer operation is expensive, so we want to save on space here. But basically what happens here is that the network is able to learn how to do that. So you need backbone to be trainable, at least the last layers of that, because if it's not trainable and the backbone outputs some good representation of the image, and then you add some random numbers to that, or some numbers corresponding to the sine positional encoding, which basically spoils the good image representation that we had. But if you make it trainable, then the network might learn that, for example, out of 256 numbers, it might use 254 for the content information, and then it will not put anything important in the last 2 digits. But then the positional encoding will zero out the first 254 numbers and then put everything it needs in the last 2 numbers. So the network might learn how much space to provide to the presentation of position and the content. That was for one-dimensional case. So in two-dimensional case, we'll basically have an X positional encoding and the Y positional encoding. Each of them will be twice smaller. So X 120. So if the overall embedding space is 256, then the Y positional encoding will be 128 in size, and the X position encoding will be 128 in size. Then for a certain cell within the image, for a certain pixel, we'll take the corresponding X encoding and Y encoding and then concatenate them, and then pass that on as our positional embedding. So that was it. Now let's go through just the visualization of what we see. So these pictures were actually achieved in, plotted in just a notebook provided by the DETR repository. So let's take a quick look at that. So here it is. It's really easy to set up. You can just use Google Colab. You can plug in any image you want from the internet or upload your own, and it will do these cool pictures for you. So it will plot the attention masks. You can drag this to visualize attention for different points. So this is the attention visualization for queries. So this is for cross attention. And if you recall, the final queries are basically the experts, and then 2 of them will correspond to some predictions, the one bird and another bird. And you can see that, yeah, like we've discussed before, the query focuses more on those elements that affect the bounding box more, like head and tail and legs in this case, and similar for the second bird. Then we can also look at some queries that didn't predict anything. So remember, if we had 2 birds on the picture and the model is good enough, it should not output any duplicates, meaning that 2 queries will output a bird, but then everything else will have to say no object. And the bounding box in this case is not participating in the loss, so it doesn't matter what is out there, but you can still visualize attention. And you can see that it's still quite close, but now it sort of focuses more on just something around the bird. And same here for another random query. So it's not focusing on a specific bird, and maybe that's why this particular query could not create a better representation for the bird. And that's why after communicating to other experts, this query sort of decided to just give up and let someone else do the prediction. Now here is the representation of self-attention. So this is attention between different pieces of the image. So this one corresponds to this one, and this one corresponds to this one. So we've seen that before. Attention for pixels that actually lie on the bird seem to focus mainly on that object, mainly on that bird. So this is like unsupervised learning of the actual object outline, which is quite cool. Then this attention for something in the background just basically focuses on everything around it. And then this one is more interesting. So again, this is a pixel from the background, and you can see that the birds are like shadows here, which is, I guess, something that will happen if you would focus on the background as well. So if someone would ask you, like, do you see something in the water, or like, what color is the water? You would look at it sort of through the birds. So you will not look at the birds at all, but instead you'll focus on everything behind the birds. So this is what we see here in this attention mask. This is the actual picture from the paper. So now we have two elephants, and this case would be particularly hard for algorithms like YOLO, because we have huge overlap between these bounding boxes. So it will probably be just filtered out by something like non-maximum suppression in case of YOLO. In case of DETR, it was able to correctly identify both objects. Again, these areas here roughly correspond to basically parts of the objects that actually affect the bounding box. And we can see here that the model also correctly understands which legs belong to which elephant. So this one is the blue one, so it corresponds to the bigger elephant. And then this leg is the orange elephant, the smaller one. So the model is able to correctly identify which leg belongs to which elephant, and that helps it draw proper bounding boxes, even this case that was hard for previous algorithms with overlapping boxes with two objects in the same spot. And this is the representation of just the location and size of the objects being predicted by every query. So here the color represents the size, so the red for large objects and the green for small, and then the purple for something in between. And this shows that, kind of like anchor boxes, queries tend to specialize. So some of them mostly detect objects in the down left corner, some of them detect objects more to the center, and so on. Unlike anchor boxes, this is not something that is explicitly encoded in the model. Instead, in the model, it's just initialized randomly, and when we and then after training, this sort of specialization is what happens naturally. So this was it about just the main algorithm of DETR. So next up, I'm going to do a reading of the source code for DETR traditionally. So if you're still unsure about how some of parts of the model work, or if you just want to get hands-on, do stick around. The next video will probably answer most of those questions.